All right, folks, and we're on another problem set, your second to last problem set for the rest of the semester. And these examples should be a quick one because all I think I really need to do for you, I probably don't even need to do all this, but if you're having trouble getting started, and that's why you're watching this video, I'm going to do number 3 for you. That one is here, okay? Problems number 1 through 5 are just like that one. We'll do it real quick, get all 5 of them done. Then we have 6, 7, and 8. Those go together. That sort of has to do with angle bisectors going on, looks like. Angle K is getting bisected, angle N is getting bisected. And then here, is that kind of a similar thing? Same diagrams have to do with angle bisector, have to do with a perpendicular bisector. Well, I don't know. I haven't read the problem there. And then finally, this one here, number 14, is the proof. So this example video shouldn't be super long. I just want to make sure I do one of the proofs with you because these kind of are some funky theorems that you can use in proofs. So you're going to use that funky theorem in number 14. But the actual problem set might take a little bit longer. So here's your problem set here. I don't think it should be too bad. Questions number 1 through 11, those should be like a minute or two each, maybe a minute. Let's say a minute. Let me stop to a minute there. So 11 minutes on numbers 1 through 11. Number 12 is a proof, so maybe take like 3 or 4 minutes on that one. It's not a super hard proof, I don't think here. 14, I don't believe is a proof. It's a word problem. 15, I think is a proof, so that's 4 or 5 minutes. It adds up, right? 17a, I think is a proof too. Maybe one of those 14 or 15 is not a proof. But anyways, 19 and 21s are proofs too. So anyways, the proofs, 3 or 4 minutes each. You at least got to draw the diagram, got to write the given and proof statement. It's got to start it at least because the ideas might come flowing to you and you might see the way to finish it before you turn it in. And if you don't finish it before you turn it in, fine, but as long as you started, it's okay. Because again, you get the Jamboard to complete your answers. Anywho, let's get into it because I said this video was going to be super long here. I got to start blabbering on. First example right here, page 140. Is number 3, right? You're just doing written exercises for this lesson. This problem set. The lesson's already done. You're just practicing today during today's classwork and homework, right? That's why it takes 40 minutes because, you should not be able to get it all done during this block period. All right, anyways, number 3 is here. Let's do number 3. It says, draw a right triangle, then draw its 3 altitudes in color. Nice thing about having grid paper. Guys, I promote grid paper all year, graph paper. In a normal year where I'm walking around the classroom, I can just point out, I'll be like, Annabella, you need to get yourself some grid paper. You need to get yourself some grid paper because you can draw diagrams a lot more clearly. So this is a lot easier to draw with grid paper than line paper because I know this is vertical because I just drew it over this vertical line on the grid. And I know this is horizontal because I drew over the horizontal line. That means I know that this is going to be a 90-degree angle. So we got this here, and now I can finish drawing it out. So I'm just drawing a large right triangle. It doesn't have to be large. It didn't say large here, so let's do it. And then it says draw 3 altitudes in color. Okay, so reminder on altitudes. What I say about that, to remember that an altitude is vertex, right? We go from the vertex, and then we go perpendicular to opposite side. Okay, or the line that contains the opposite side here. So this is shorthand I have for remembering this. Hopefully you got that out of the exit ticket. You can concisely say that a median is going from a vertex to the midpoint, vertex to midpoint, vertex to midpoint, vertex to midpoint. That's a median for a triangle, and triangles 3 medians. Vertex to midpoint at the opposite side. Altitude is vertex. Draw that line, draw that segment perpendicular to the line containing the opposite side. So vertex to perpendicular, right? That's what I say it for short. Vertex to perpendicular, that's an altitude. Finally, perpendicular bisector has nothing to do with the vertex. So perpendicular bisectors might come up in these questions 1 through 5. Remember, a perpendicular bisector is of a segment. It's not necessarily of a side of a triangle. So sides of triangles are segments, so they do have perpendicular bisectors, but any segment has a perpendicular bisector. It's the line that's perpendicular to the segment at its midpoint. So it's unlikely that a perpendicular bisector of a side of a triangle, remember that's just a segment, is the side of a triangle. It's unlikely the perpendicular bisector will go to the vertex here. Okay, so that's one way to differentiate between altitudes, they start from a vertex. So here, there's a vertex right there, and they go perpendicular to the line containing the opposite side. So let's take a look at this here, this diagram, because if I went perpendicular to this side here, I wouldn't actually be going to the side, I'd be going to the endpoint of the side here. So here, if I extend this, right, this is the line, right, the line here that contains the side here. So my altitude, I want to draw to that line perpendicular to it. And if I do that, I'm actually going over this other side here. Here is an altitude. Boom. How do I know it's an altitude? Well, it goes through a vertex. right? This top vertex of the triangle. This is an altitude here in red, and it's perpendicular to this line here that contains this side of the triangle, right? This side of the triangle here. So this meets the definition of an altitude. Through a vertex, perpendicular to the line containing this side of the triangle, okay? So let's look at the other ones. Let's check the other ones out here, okay? Let's check the other ones out here. What about this point here? This is definitely a vertex of a triangle. Here's the vertex here. Okay, so here we have side 1, side 2, side 1, side 2. Are those either these sides of the triangle, the opposite side to that vertex right there? No, opposite that vertex, we have this side, okay? We can't draw, look at this, we can't, in a right triangle at least, we can't draw an altitude inside of the triangle, in the interior of the triangle, because look, this isn't gonna be perpendicular to the line containing the opposite side, so I gotta draw it like this. Right, here is my altitude number 2, okay, is right here. So once again, it's not inside the triangle, and it's just gonna hit the end point of this side here. So notice this here, this altitude, these two altitudes actually converge where? In the third vertex. The vertex of, right, vertex of the right angle in the right triangle. So that is an interesting takeaway. That is definitely an observation here that you might get asked for, is that, well, where do the altitudes converge in the right triangle? Well, you can sketch it out, you can figure it out on your own, or you can just remember that. They're gonna converge, right? They're going to be concurrent, this word called concurrent, at the vertex of the right angle here. And we'll see that once we get the third altitude. So we have altitude right here, and let's get the third one down here. So what we have for the third one is, again, what do we have? What's an altitude? It's a vertex perpendicular to the line containing the opposite side. So I didn't write that out because I'm trying to abbreviate it, right? Your notes, sometimes you abbreviate things. You should know everything that's in the definition. But here, when I'm writing it out to you guys and I'm referencing it, I'm writing it short here. So I got a vertex, and here's the vertex. Remember, this is the whole thing. This whole freaking thing was in blue earlier. So we have a vertex right here. Remember, the whole thing was in blue here. This was a vertex of the right angle. And that's, of course, an angle of the right triangle, right? It have to be a part of the triangle here. And if I draw the altitude here, I got to start there, right? Because it starts vertex and it goes perpendicular. And here it could be kind of hard to see. You can figure out maybe slopes, right? I've done that in Algebra 1, opposite reciprocal slopes, perpendicular. But hey, we're just sketching it now. We're just sketching it. So let's check it out here. So yeah, just kind of eyeball it, right? Eyeball these questions here. Boop. And right, we go vertex aside, and I probably shouldn't have done it because an altitude is technically a segment that connects, that goes vertex to opposite side. So I'm actually going to erase these things here, except for maybe this one. I'll go vertex to opposite side, and I'll go perpendicular. I'm sliding. This looks perpendicular. Okay, there we go. And here, my friends, is an altitude. It's actually the only altitude I've drawn so far because the other two are not altitudes. Can you tell why? I messed up. And altitudes are defined as the perpendicular segment. Here, perpendicular segment to the opposite side. So I didn't even write it there. So I shouldn't have actually drawn that altitude so far. I just erased some of the triangle right here. Didn't mean to do that. Let's get the triangle back up here so we see the right triangle again. The altitude is not up here again. I got to erase it. The altitude is the perpendicular segment from a vertex to, oops, I meant to change that here. Vertex to the line containing the opposite side. So this is what I should have drawn here. Look, this is a segment from vertex perpendicular to the opposite side's line, right? Opposite side's line right here. And then last one here. You might be wondering, Mr. Ford, why'd you erase this? It's because I didn't draw segments. I should draw segments. The altitudes are defined as segments that do this, right? They're perpendicular. They're drawn from the vertex to the side perpendicular, the line containing this side opposite. Okay, that was pretty wordy here, but I want to show you that because that's kind of neat here. Okay, that's kind of neat here. That, right? If we have an altitude of right triangle, right? If we have that, an altitude of a right triangle, right? Then I want to do plural. If we have the altitudes of a right triangle, then we know that they're going to be concurrent at vertex of right triangle. And it is possible to prove that deductively, but we're not going to bother with that right now. It's just an observation we have there. And yeah, Altitudes logically would do that, right? They would, because it's got to go through that vertex, and yeah, you just have to be at a right angle when we get to the side here. So yeah, totally here. Okay, so right, when we see three lines all in the same place at the same time, we say that those lines, two or more, more than two lines, so three or more, we would say it's concurrent. Okay, concurrent here at vertex of the right angle. All right, anyways, there's our number 3. All you really had to do for number 3 was draw the freaking diagram. Draw the diagram, draw the 3 altitudes, and then you're good to go, right? Just a quick problem. A minute. I talked for a while because maybe you want to get the juices flowing, you want to put the ideas down on paper, you want to listen to good old Mr. Forn explain this, and that's why you're watching it now. But if not, yeah, I don't know what you're doing here then. I don't know why you're watching it here. If you don't care to watch this, why are you watching this video? Anyways, let's check it out here. Number 6 here. If x is on the bisector of angle K, so if this is an angle bisector, I'm going to do that just to remind me we're dealing with an angle bisector here, right? Angle bisector of angle K. All right, there we go. Then x is equidistant from, well, let's see here. Is x the same distance from N and S? No, x looks further away from S than N. That doesn't make sense. What's the deal here? What do we remember about angle bisectors? Angle bisectors, what do they do? So if you're a point, here we have a point, okay, here we have a point that's on the angle bisector of an angle, okay? So we have a point on the angle bisector. What do we know? What's the implication there for that point? It's going to be equidistant from what? The sides of angle K, right? The sides of angle K. Okay, so here x, and you got to remember the way that we measure distance, right? So the sides of angle K are pretty obvious. The sides are ray RS and ray KN. There is angle K in this diagram right here, right? Of course, we added on this angle bisector, but before we add this angle bisector, this is angle K right here, or angle SKN. That's the one being bisected. So we have a point here, and it's equidistant from the sides. This side here is KS. This side here is KN. So the question is, how do we measure distance, right? Distance is measured. This is measured what? Distance from a point, and in this situation, it's x, to a line or lines, which we could do line SK. And in this one here, we care about, well, let's do KS because it's ray KS we care about. KS and KN. How do we measure the distance between those two? It's the perpendicular segment. Okay, the perpendicular segment can be drawn, right? So here, remember, this is the one, if you're on an angle bisector, this distance to this side of angle K, right? This is a side of angle K. And this distance here is defined as the perpendicular distance here to that side here, okay? So you're not going to measure distance from point X to this side here by measuring a segment like that, measuring a segment like that, measuring a segment like that, because those are longer, right? Those are bigger than this. This is the fastest way we can get there. The minimum distance from the point X to here is the perpendicular, so that's what we say, that's the distance. That's how close we are to the wall, right? To the ceiling, right? The ceiling is perpendicular above my head, not over there, right? Not over there, not over there. Okay, so this here is the distance from here is gonna be, the perpendicular distance here is the same as the perpendicular distance over here. And that was proven to us. I believe it was AAS is the way we proved it. Drop in your perpendiculars here. That's an angle, that's an angle. This is another angle, that's another angle because this is an angle bisector. And here, KX is equal to KX. So this is AAS, AAS, or SAA, SAA. Okay, so anyways, but the key reason, the key thing to know about this one is that X is equidistant, yoink, yoink, from SK, or I should do KS. I should do ray KS because the side of an angle is a ray, right? Because an angle is defined as two rays that meet at a common endpoint, thus being the sides have got to be rays. So you have ray KS and ray KN is your answer right there. That's what we're looking out for when you do the Jamboard on Wednesday here. All right, check this one out here. X is on the bisector of angle N. How about that here? All right, same thing, different day. Different day. Same thing, different day. That's how the saying goes, right? All right, X is in the bisector of angle N. X is equidistant from, well, drop a perpendicular there. drop perpendicular there, right? We would know that it's equidistant from what? And our answer here is ray ns and ray nk. And we're good to go, right? Quick problems, right? Quick problems. That might cause you a little time to think about. That one's super quick. This one, let's see if this one's quick here. If x is equidistant from SK, segment SK, and segment SN, then x lies on what? Okay, so let's draw it in maybe. If SK, how do we measure distance? Okay, right? If we're going, if x is equidistant from SK, right? How do we measure distance? Okay, the distance would be the perpendicular segment, right? Length of perpendicular segment to that segment's SK. So let's do that here. So I got that perpendicular segment. That looks perpendicular enough to me. There we go. There we go. Okay, if x is equidistant from SK and SN, SN's over here. So I will draw the old segment in here, the old segment E, and there we go. Sure, why not this? Okay, so x lies on the, it's not drawn in here, the perpendicular, x lies on the, here we must have proven this, okay? It must lie on the, let me introduce the angle bisector of angle K, yoink, yoink, and if this is the angle bisector of angle K, x has got to lie on it. And we would get it because, well, this is a angle, this is a right triangle. We would know that those angles are correct, are the same here. We have a hypotenuse here. What do we know? Oh, it's equidistant. So right angles get us right triangles, and it's equidistant. So we get this as a leg. So here and then here, SX equals SX by reflexive. So here you'd have a hypotenuse leg, right? See, this hypotenuse is congruent to that hypotenuse because this is the same thing in that top triangle versus the bottom triangle, and then it's equidistant. So we know that x perpendicular to the side here is the same as x perpendicular to the side up here. So those legs are congruent, hypotenuse leg, and their hypotenuse leg is good because we know these are two right triangles are congruent, and that means that this has got to get bisected, right? This has got to get bisected. Angle S here lies on the angle, right? When you say bisector, you try to say whether it's an angle bisector or a segment bisector, okay? This is an angle bisector of angle S. And there you have it. All right, 14. I've had enough coffee today. Let's have some more coffee. 14, let's see if we can wrap this one up. Given S is equidistant from E and D. So I'm just marking it up, right? It's nice for me. I have the pictures all freaking up here, but you should write this out in your notebook, sketch it out, right? You get to know the diagram just by sketching it all out. It takes a minute, right? It takes a minute. That's why sometimes I showed you it takes a minute. And V is equidistant from E and D. But you can mark it up, and then you can notice a few things here. So what is it we want to prove? We want to prove that SV is the perpendicular bisector of segment ED. How are we going to do that? How are we going to do that? A few ways we can do that, perhaps. A few ways we can do it, perhaps. Okay. Who's got a way? Let's see here. Who has got a way? There's a few. I like this one. There's a lot of ways you can prove this one potentially. Okay, we have this one up here. The question is SV. So the thing that we need to prove, let me maybe circle. We haven't proven this yet, so I'll put question marks on here. We haven't proven whether SV is the perpendicular bisector. So I'll put a couple more tick marks. 1, 2, 3. We want to prove that. We want to prove that, and we want to prove that. So how do we do that? How can we prove that? There are many ways we can prove this. Actually, I'm going to show you one way involving congruent triangles. Lovely. No, is it congruent triangle? I don't know, actually. I don't think I can prove these triangles congruent, come to think of it. Yeah, there's only a few ways. There's only one way to do this, I think. I can't prove these triangles. Well, let's see here. Ooh, actually, never mind. I see it. Ooh, this is a fun one. I might have somebody present theirs tomorrow. Okay, I'm going to prove it using congruent triangles, and then I'm going to show you another way to prove it here. So this video is going to end up being a little longer. I was thinking it was a fast one. I thought I would get out of here. All right, statements, reasons. S is equidistant. Right, you can use the vocabulary by writing it down from E and D. V is equidistant from E and D. This is given. Step 2, Okay, I found some congruent triangles. Did you find some? Well, check this out. What can we say about that side? SV equals SV. How does that help us? SV equals SV. Helps us by reflexive. Well, it doesn't help us by reflexive. We can say it by reflexive, but it helps us find two congruent triangles. Who sees it? Who sees it? If SV is equal to itself, how can I then prove two congruent triangles? Well, I should say this. I should say definition of equidistant. Okay, so check this out. Definition equidistant. Okay, equidistant. I should probably say this. SE equals SD, and VE equals VD, and that's definition of equidistant. Your book doesn't actually define equidistant for you, but logically that's what it means, is the equal distances from things. So if your equal distances from point E and D, then it's just whatever your point is and to whatever that point is going to be the same as from that point to what the second point you're equidistant to. So anyways, this is the definition of equidistant. You're welcome to use that as a reason and a proof. I think it's good here. So now I actually find congruent triangles. Look at, I have a side, side, side correspondence. We just got to name the triangles here. So I got triangle SEV congruent to triangle SDV. And that is SSS. Okay, step 5. How does that help me? Well, if I could actually prove that this triangle is congruent to that triangle, then through CPCTC, I could prove that here, let me do EZ perhaps. I have to actually add a point. It's okay to label a point. I'm just labeling a point here. I'm not adding it to the diagram. So I'm labeling it as point Z. And that's where SV intersects ED. That's the intersections of point Z. So anyways, I could prove that that triangle is congruent to that triangle in a second, because I could say through CPCTC, I could say this angle congruent to that angle, right? They would correspond here. Angle ES Z would equal angle DSZ, because they're corresponding parts of congruent triangles. So I'll do that real quick. I'm just showing you the longer way of doing it. I'm going to show you a real fast way of doing it here. So we got here angle ES. I'll do ESV because we're doing the V's up here. Congruent to angle DSV, and that's through CPCTC. And now, check this out. Now I have triangle E. Well, I gotta do reflexive here. See, these proofs can get out of control really quickly. And I'm gonna show you a much faster way of doing it. SZ, and that's reflexive. Okay, so now here I have SAS. I got these two triangles, top triangle congruent by SAS, because I just got the reflexive action. 4 tick marks there. Okay, so then let's do this. Triangle ESZ congruent to triangle DSZ, and that is by SAS. Okay, and that's going to help us prove that this is going to get perpendicularly bisected, because here we have, wait a second. This would have been so much faster. Oh, man. Oh, Sport is doing way too much work here. Let me pause the video. I'm going to show you 2 really fast ways of doing this. Oh, man. Got to solve these puzzles. Like, the more you practice, the faster you can solve these puzzles. Let's check this one out. Pause the video. All right, and we're back. So I got the diagram reset. I'm going to bail on this proof up here. I could have proved it earlier over here, but I realized I missed a theorem that could get us to a lot faster. Anyways, statements, reasons. Okay, well, let's just take our givens right now, because I already wrote them down again, just so I don't want to save your time. So we'll do our givens. Please don't do this when you're writing proofs. Don't put that down there. And write it out. Get to know what those things say. All right, givens. Let me remark it up here. I'm actually only going to mark up this. So I'm going to mark up S is equidistant from E and D. That's all I need to actually prove this. Boom. Boom, okay? And then maybe I'll say that in the proof, right? I'll say this, that ES equals DS, and that's by definition of equidistant. Okay, and then step 3, Because I know that, I'm not even going to bother with the V is equidistant from E and D. Because I know that, actually, check this out. What type of a triangle is triangle SE? Straighten out. It didn't straighten out. SED. Triangle SED. What type of triangle is that? What do you notice here? Right, I just established it that ES equal DS. So what triangle is that? It's triangle SED. Yeah, triangle SED is an isosceles triangle. Okay, and that can be step 3 of our proof. And why is an isosceles triangle good? Oh, no. Oh, man, Mr. Fortin. Let's go back to the drawing board, guys. Let's go back to the drawing board. All right, this is why I needed to do all this work. Now I realize why I needed all this work. Okay, check this one out. Okay, so I actually did need to get that triangle congruent to that triangle. The reason is because I need to get that angle's congruent to that angle. And did I say that at any point in time? Did I? Oh, I did say it earlier in the proof. Oh, good God, you guys are actually watching this. This is wild. This is nuts. All right, anyways, I said that that angle is congruent to that angle. So what we have here is that angle ESD is the vertex angle in a right triangle. Okay, maybe I'll just put this down here. I'll pull this reason from earlier, which is this, SE equals SD. Okay, and I'm just going to say this now, so just stay with me. We've said all this stuff here, and the key thing is that I want to get triangle SED is an isosceles triangle. And that's good because ED is the base of an isosceles triangle. What do we know when we have an angle bisector of the vertex angle of an isosceles triangle? You see it? You see what I'm thinking? You see what's going on in my head that I'm trying to communicate to you guys here? Okay, that's definition of isosceles. Okay, I'm trying to get through here is I've already said angle ESV is congruent to angle DSV. So that means that SV is the angle bisector of the vertex angle of the isosceles triangle. So let's say that in the proof here, because I've already said angle ESV is congruent to angle DSV. So now I know that ray SV is the angle bisector of angle ESD, and that's definition of angle bisector. Okay? And that's important because when you have the angle bisector of the vertex angle of an isosceles triangle, okay, what do you know it's going to do? It's going to be perpendicular to the base of the isosceles triangle at its midpoint. And that's good because that's the whole goal here. I'm trying to prove that line SV is going to be the perpendicular bisector of segment ED, which is the base of that isosceles triangle. Okay, so let's wrap this up, and I'm going to show you a real fast way to do this proof right here. And you're going to be so mad that you spent so much time watching this video. So let's check this one out here. So what I know now is that ray SV, or the line that contains it, line SV here, is perpendicular to line ED at we'll put point Z, and therefore we've concluded, because there's an angle bisector earlier, that Z has got to be the midpoint of line ED. Okay, and that is step 11. Whew. Okay, you run a space here. The bisector of the vertex angle of an isosceles triangle is perpendicular to its base at its midpoint. Okay, and that's good. Okay, we have line SV. It's perpendicular to the base, so that's line ED at the midpoint of ED. So what do we know it is? It's a perpendicular bisector. And that's the exact here. Step 10, we've just said all the information that requires to establish something's a perpendicular bisector because it's perpendicular to the segment at its midpoint. That's what a perpendicular bisector is here. So we can say that SV, we can wrap up our proof finally. SV is the perpendicular bisector. of segment ED. And that is definition of perpendicular bisector. Okay, so you might be like, Mr. Fortin, really? I have like 6 of those proofs? It's more like, it's not 6, it's like 4 or 5, right? 3 to 4 minutes each. Like, am I really expected to do all that and get it all done? Well, challenge yourselves. Do it if you can. Get into these puzzles here. I'm running out of time. But some of these proofs can be done a lot faster. So maybe just give it a shot. Go down the wormhole a little bit. Try to figure some stuff out. Look around. Poke your head around. And then when you get to the Jamboard, hopefully someone in your group has a faster way of doing it, and that can be a good way to study from, okay? So it's not just like getting one puzzle done. I want you to see the various different types of puzzles that are out there in the world here, because I'm going to give you a faster way you could have done this. I'm going to pause it for a second and get a picture back here, but here's going to be a faster way. All right, and maybe this faster way jumped to your head right away. If I know this, SR1, here, I can say my givens. Okay, my givens are right here. And I'll write given. Please don't do that in your homework. Get to know this. Like, just only because I've written it already once. I'm not writing it again here. Okay, so if I know that S is equidistant from E and D, I would know that. V is equidistant from E and D. So what I actually know about this, and this is sort of where your brain probably went with it here. I showed you the harder way because some people just want to find congruent triangles. You have some theorems to make your lives a lot easier here. Because what do we know about point S? What do we know about point V? Other than they're equidistant from 2 points here. We know they're equidistant from the endpoints of a segment. So what we know is that S and V are both on the perpendicular bisector of segment ED. Segment ED. And the reason why I know this is if a point is equidistant from the endpoints of a segment, then that point, and we're saying about 2 points if this is true, then that point is on the perpendicular bisector of that segment. Okay? So we know S and D have to be on the perpendicular bisector of that segment. So how do we know that line SV, this one right here, if point S is on the perpendicular bisector and point V is on the perpendicular bisector, how do we know that all those points are on the perpendicular bisector? Well, that point's on the perpendicular bisector. So each segment has one perpendicular bisector, which is a line, right? As one line that's perpendicular to that segment at its midpoint. So why do we know that line SV is that one line? Well, both points are on the perpendicular bisector, and through any 2 points, exactly one line can be drawn. So that is the only perpendicular bisector. That is the perpendicular bisector. Both S and V are on it. I can connect the 2 of the points. I found the perpendicular bisector here. So there it is. 3-step proof, actually. And you might be wondering, am I saying everything if I did it this way? Yes, you have. Okay, SV is the perpendicular bisector of segment ED. And that is, reason for that is, well, through 2 points, there is exactly one line. So that guarantees that the one line, one and only one line, the uniqueness of that one line connecting those 2 points you already know are on the perpendicular bisector, that line itself is the perpendicular bisector, because that's the only line that could be where those 2 points can be on it, right? There's no other line there, so that is the perpendicular bisector, okay? There's your video. I hope you proved it the 3-step way. I do enjoy showing it to you the longer ways because you can see even how the best ones get tripped up. I knew that I was going to do it the wrong way first, but I assumed that you guys were like, I feel like I can see this, I can get this using triangles, and it turns out you can, right? If you re-look through my logic, maybe you'll see it and see I could have done this with triangles as well, and it's fun to solve the puzzle with triangles, but what's better, if you have some theorems that allow you to get it to a lot more quickly here. And this theorem, or this was a postulate back from chapter 1, where that comes into play here, okay? Hope you enjoy the rest of the problem set. Do the best as possible to problem solve, to puzzle solve, right? Get through those puzzles here. If not, you're going to keep practicing that on the Jamboard on Thursday. Take care, guys. Have a good day. Bye.